Hello everyone, my name is Mert. I'm a PhD student at Texas Tech University. In this talk, I'll be introducing our preliminary work on Towards xBGAS on CHERI, supporting a secure global memory. My co-authors are Brody Williams, John Lydell, Jonathan Woodruff, Simon Moore, and Yong Chen. This work was made possible thanks to a collaboration between Texas Tech University, Tactical Computing Labs, and the University of Cambridge. To give you a sense of this preliminary work, I'll start ahead with some background, motivation, and then methodology. Nowadays, reducing latency on operations over remote nodes are more critical than ever. The transition from monolithic architectures to scalable systems introduced challenges for supporting interaction across these components. The Extended Base Global Address Space project offers an extended addressing model to the standard RISC-V ISA through a microarchitectural extension. xBGAS has been shown to increase the performance of PGAS models significantly. In parallel to our work on xBGAS, University of Cambridge has been working on CHERI as a hybrid capability architecture that blends architectural capabilities with hardware-supported descriptions of permissions on pointers. CHERI allows traditionally memory-unsafe programming languages such as C and C++, to be adapted for providing efficient protections. CHERI led to the development of a ARM Morello platform that is CHERI-enabled. Our work presents initial research into building a secure PGAS programming model as a step towards integration of xBGAS and CHERI architectures. I will now give some quick background on xBGAS. xBGAS stands for Extended Base Global Address Space. It is done as a collaboration between many institutions. The goals of xBGAS is to provide 128-bit extended addressing capabilities based on RISC-V architectures, but the RISC-V 64-bit apps still execute without an issue on extended systems. Extending addressing for xBGAS is flexible enough to support multiple target applications. Extending addressing does not specifically rely on any one virtual memory mechanism. Therefore, the concepts of xBGAS is portable to other platforms as well. Here is a figure depicting the overview of the xBGAS architecture on two different cores that are xBGAS enabled. You can see that a processor in node 1 can communicate through the network interface between the memory space of the node 2. On another note, CHERI is an architectural protection model that is composed with both hardware and software that adds new security primitives to the base ISAs and is implemented by microarchitectural extensions. Here in the figure you see a CHERI FPGA prototype. CHERI enables new security behaviors in software and it mitigates vulnerabilities on trusted computing bases. CHERI is implemented on a prototype platform that is based on ARM Neoverse called Morello. Morello boards offer some real-world test platforms for some experimental features. This platform could provide us with better hardware prototype that would expand our work securely beyond software simulations. Here you see the depiction of a CHERI capability representation. This will come in handy when we compare it with the xBGAS pointers. xBGAS on CHERI has some of the core motivations that drove our research on xBGAS, such as scalability, generalizability, and keeping software overheads low. However, on this project, we also want to add some security benefits that CHERI can bring to xBGAS platforms. Porting the xBGAS runtime library onto CHERI-enabled Morello boards consists of work on 4 different main abstraction levels that are shown in the figure below. This involves selecting a simulation platform to represent the hardware, doing some translations on the low-level runtime of xBGAS, and adapting the xBGAS API to support such calls. And we need to keep the changes on the xBGAS applications and benchmarks to a minimal to be able to demonstrate the platform. Thus far, we have been using ARM's Fixed Virtual Platform, otherwise known as FVP, for our hardware simulations. We have also investigated the potential of using the Quick Emulator, QEMU, for the Morello platforms that are offered by the University of Cambridge as our evaluation platform. As the operating system on our platforms, we have been using the CHERI BSD with the pure capability enabled CHERI C compiler. Some of the challenges with this work is to figure out the inter-process communication model that would be suitable for xBGAS without breaking the validity of capabilities for CHERI. This is because the remoteness of the data needs to be communicated across different PEs for xBGAS to work. Regarding the hardware requirements, xBGAS's need for an arbiter can be simulated via a software abstraction. Nevertheless, the namespace look-aside buffer functionality requires some bits on the memory interface to encode the data location. To do this, we propose using capability object field on the CHERI architectures, on the CHERI pointers, to encode remoteness information. Sacrificing 15 bits from this field would offer over 32,000 unique IDs for remote nodes that would be sufficient for node-level prototyping. Here is a comparison between the xBGAS and CHERI pointers. Our proposal is to send capabilities between nodes in a method that is not necessarily less privileged than the low-level CHERI states. An idea of transferring capabilities is to separate the upper bits and the lower bits of the xBGAS pointers into two and send them over through those methods. To make these simulations possible on a single node Morello environment, we decided to use pthreads to represent different PEs. We have implemented thread pooling to achieve concurrency during the execution of this program to simulate multiple different PEs. Here is a flowchart that represents the thread management, the thread pooling idea that we use to simulate multiple threads that represent multiple PEs on the Morello platforms. This method allows us to restrict the creation and destruction overhead of threads to the initialization. And the work units are here representing the smallest unit of task that can be fed into a thread, whereas the work queue itself is just a singly linked list that assists the scheduling of work units. Currently, on xBGAS, data communication is accomplished by one-sided remote get and put calls between different PEs. We evaluate the feasibility of our porting effort by testing the sequential get and put calls between different threads. These functions need the xBGAS extended load and store assembly instructions. And the function prototype is shown below as an example. Up until now, the xBGAS runtime was designed to run on RISC-V systems. Therefore, it relied on some RISC-V specific assembly instructions, including the extended instructions proposed by the project itself. To have a demonstration or a prototype, we need to come up with the equivalent translations of these instructions to the ARM Morello platforms. Here you see one of the examples of the translations that we have already implemented. Note that we currently do not have support for extended instructions on ARM Morello platforms. To showcase our proof of concept, we have identified some of the common function calls that is likely to be seen on any xBGAS benchmark or application. Here are some of these functions shown. For example, the xBRTime_init is the initialization function that needs to initialize the xBGAS runtime environment for every xBGAS application on or benchmark. Here you can see the xBRTime_malloc to perform a memory allocation. Some other common functions are the xBRTime_YPE, the xBRTime_barrier, xBRTime_number of PEs, xBRTime_get and put instructions for all different sizes of transfers, xBRTime_free, and xBRTime_close. In addition to what is shown here, we have also implemented a constructor and a destructor for all the xBGAS applications to be called upon the start and finish of an xBGAS application. In a nutshell, the goal of xBGAS on CHERI is to build secure large-scale systems that maps shared data blocks into the extended scalable address space by utilizing some ISA-level remote data operations to access data directly. Offering scalable software compartmentalization and fine-grained memory protections is a must to ensure the secureness of these systems. CHERI would bring us the ability to implement memory-safe C and C++, which would mitigate the use of their free vulnerabilities, even in the case of xBGAS applications. To conclude, this work presents the preliminary research behind the step towards a more fundamental integration of xBGAS and CHERI architectures. Although this work does not provide performance results on the xBGAS infrastructure, we have presented the methodology for achieving a lightweight runtime on CHERI platforms. Currently, using our simplified runtime, we can demonstrate xBGAS applications for matrix multiplication and gather operations. We are now implementing the inter-process communication ideas and integrating our thread pool library, which we have introduced on this paper. Please see our paper for more details on the xBGAS on CHERI project. Thank you for your attention. Let us know if you have any questions. Here you can see my email, the link to some of our artifacts, and the ongoing work, including the runtime on xBGAS. Thank you.